Hello viewers, welcome to my video lecture. In this lecture, I will explain about the image retrieval on the basis of the color features and the discrete wavelet transform. So let me show you the contents which I am going to cover. First, I will introduce the topic, that what is the content-based image retrieval, CBIR. Then I will explain the proposed algorithm which is based on the color edge features. And then I will explain the training process where we will find the feature vectors of all the images in a database, and then I will explain the testing procedure, and then I will give the MATLAB implementation of this project with the MATLAB code, and in the last I will analyze the results. So let's go ahead. But before going ahead, I recommend you to watch following my 3 videos which are also based on the CBIR. The first one is about the color layout descriptor CLD, which is of MPEG 7. It is widely used for image retrieval on the basis of the color features. The second one is the edge histogram descriptor EHD, that is also of MPEG 7. This is also widely used to retrieve the images on the basis of the texture features. And on the basis of these two, I mean CLD and EHD, I have implemented one complete CBIR system which I have explained in this third video. So you can go through all these 3 videos to have the better exposure about the implementation of the complete CBIR system. So the links are given in the description. So now let's come to the topic. So let us see what is CBIR. The CBIR, also known as the QBIC, I mean the query by the image content. It's a process of retrieving the expected images from the large image database according to the contents of the query image. So the contents mainly refer to the color feature, texture feature, or the shape features of the query image, which can be automatically extracted from the images using the various feature extraction algorithms. So CBIR is different than traditional search, which is based on some metadata such as some keywords, some tags, or some descriptions associated with those images. The keywords also limit the scope of the queries because of some set of the predetermined criteria, but the CBIR is quite flexible. It focuses on the search on the basis of the contents of the query image, and it has no predefined criteria. So this is the overall scheme of the CBIR, where we can see that we have image database which has lots of images. With the proposed algorithm, we extract the features of those images from these images. And then once the features of all the images are extracted, those features are stored in the feature database. So now when I give a query image and I want to retrieve the similar results, which are based on the contents of this query image, the features are also extracted for this query image by the same algorithm. And then this feature is compared with features in the feature database. And on the basis of the similarity, we get the nearest match results as the output. So that is the overall scheme of the CBIR. And now let me discuss about the proposed algorithm, which is based on the color edge features. So in this scheme, the image retrieval is based on the color and edge features together. So for this purpose, we have the color RGB image, which is first represented in YCBCR color space. This is done to separate the luminance and the chrominance details. So as we know that Y carries all the intensity detail, I mean the luminance, while the CB and CR carry all the color details, I mean the chrominance. So to get the edge features, we apply the Canny edge detection on the Y component. So after applying the Canny edge detection, we get an edge map. While the CB and CR are left unchanged, we do not apply anything on those components. So once we get the edge map after applying the Canny edge detection on the Y component, we replace the original Y with this edge map. And then we combine this edge map Y together with the unchanged CB and CR, and we retrieve our RGB image back. So In this RGB image thus obtained, the color information is not changed because we have not modified CB and CR. Since Y component is replaced by its edge map, therefore this RGB image has the edge details along with the color. So this is the overall scheme you can see. So let me say I have the input RGB image IMN. This is first decomposed into the Y, CB, CR three components. Then we apply the canny edge detection on the Y component, while CB and CR are left unchanged. So once the canny is applied, we get this edge map Y edge. Then with this Y edge and the unchanged CB and CR, we combine these three matrices to get the Y, CB, CR modified by CB, CR image, and then converting that image back to the RGB, we get the RGB color image, which has the color information as well as the edge informations which are more emphasized. So this is my output image, let's say I-MN. So this is the output of this proposed scheme. So this is your input image, which is RGB color image, and this is the edge map of the Y component of this image. Okay, so the original Y is replaced by this edge map, and then it is converted into the RGB again. So this is the output image. Here you can see that colors are there, but edges are also highlighted. So this is image which has the color information as well as it has the edges which are more emphasized now. So now we will find the feature vector of this image. So for that we are using the wavelet decomposition. So let's see how the wavelet is helping us to get the feature vector. So now what are the next steps? So to get the feature vector FV, we first find the histograms of the RGB component of this image, which is obtained in this previous stage, that is I-MN. So this image I-MN is broken into the RGB components, and the histograms of each components are found. So let's say these components are HR, HG and HB respectively, means HR for R, HG for G and HB for B component. So these histograms are of length 256 because each component is a grayscale image. So total intensities are 256. So we are finding a full length histogram for each RGB component. So reduce the size of these histograms, we are using discrete wavelet transform. So here the HR and HG are decomposed in the discrete wavelet coefficients up to the level 2, while the HB, which is the blue histogram, it is decomposed up to the level 3. This is we are doing because as per the human visual systems, the red and green has a more importance in the perceiving the details, while the blue is not so important in the human visual system. So blue is more decomposed, I mean up to the level 3. So even if we lose some details in the blue histogram, it will not affect the system's capability. So now what we do, we extract the approximation coefficients of HR, HG at level 2 and approximation coefficients of HB at the level 3. So let these are represented by FVR, FVG, FVB. Why we are taking approximation coefficients only? Because the detail coefficients are the noisy coefficients. They don't have the details. I mean, they don't have the shape of the histogram. The shape of the histogram is preserved only by the approximation coefficients, right? So by doing the wavelet decomposition, the length is reduced. For example, if I take one label decomposition, the length of 256 will be reduced to the half, 128. So that's why the shape is preserved, but the length of the data is reduced. That's why we are taking the approximation coefficients. While detail coefficients, they are just noisy, so they don't serve any purpose. So we are leaving them. So due to the second level decomposition, the 256 length, as I said, it's reduced to 64. Why? Because 256 in first decomposition reduced to 128, Then second level decomposition, the 128 is reduced to 64. And the third level decomposition definitely will be reduced to 32. So the length of FVR, I mean the histogram of the red channel will be of the length 64 because of the two level decomposition. Similarly, it is the length of the green histogram, but the blue is decomposed up to the level 3, so the length of FVB is 32. So to get one feature vector FV for an image, we concatenate all these histograms, I mean approximation coefficients at label 2 and label 3. So when we concatenate like this, the size of the feature vector is only 160 because this is its length is 64, its length is 64, and the blue coefficients are of length 32. So 64 plus 64 plus 32 is 160. So 160 is a small number as a feature vector. So because of this small number, it will assist us in a faster search. And also, if we store the features of all the images in an image database, definitely we will get a smaller feature database. So that will have the less memory requirement. So the proposed scheme is better in the sense of the speed of the search as well as the less memory requirement. So here for the wavelet decomposition, we have used the Quaeflet 5. I have used this on the basis of the experience, and I'm getting good results. One can go for some comparative analysis if they are interested in using the different wavelets. So this is the overall scheme of actually getting the feature vector. So this is the stage 1, which we have already seen, where the input RGB image is converted into the image with edges I-MN, which we have seen that how it is decomposed in the YCBCR. Then Y channel, we apply the Canny on Y channel and then combining those YCBCR to get this image. So it is already discussed. So this is the stage 2, which I have just discussed in the previous slide. So where this I-MN is, as I said, decomposed into RGB channel. Then we find the 256 bins histogram for R. So that is HR. For G, it is HG, and for B, it is HB. At this moment, the length is 256 for each histogram. So if we get a feature vector from these histogram, the length of the feature vector will be very large. I mean that will be the 256 into 3. So to get the smaller size feature vector, I'm using the wavelet decomposition. So the red histogram is decomposed up to the level 2. And we are taking only the approximation coefficient, so we are getting the length of 64 only. Similarly, we are applying the level 2 wavelet decompositions on green histogram, and we are taking only the approximation coefficients, so we are getting FVG of length 64. Then we are applying the three level wavelet decompositions on blue histogram, and we are getting only the approximation coefficient, so FVB has having length of 32. This I have already told you that why we are getting the approximation coefficients at level 2 for red and for green, and the third level decomposition for the blue. Because if you go for more decomposition, your number of coefficients will reduce, as you can see. So that means you are losing some details in the shape of the histogram. But as per the human visual system, we know that the blue has the least contribution, while red and green are very important for the image color. So to reduce the size of the feature vector further, we can extend our reduction in the size for the blue channel only. If you go for more reduction in HR and HG, your accuracy will be affected. So now we are combining the FVR and FVG and FVB to get the complete feature vector of 160. So this combination is nothing but it is a concatenation. So this is how you are getting your complete feature vector. So now let's see the output of this second stage. So this is the image which I obtained in the first stage. Okay, so this is decomposed into the RGB channel, finding histograms and then decomposing into the approximation coefficients, red in second level, green in second level and blue in third level. And then combining or concatenating those approximation coefficients, you are getting this type of feature vector. Okay. So obviously this is your red histogram, this is green histogram and this is blue histogram, but they are of length, this one is 64, this one is 64 and this one is of 32 only. So total length is 160. So this will be stored as feature for this input image. So this we will do for all the images in the feature, image database. So that will be simply the training procedure. So this is the training procedure you can see. So here I am taking one image database which has total 210 images. So I am taking a database which has images of flower that I will show you in the next slide. So we find the features of all these 210 images, and each feature, as you have seen, it is of 160 length. So the total size of this feature database, X matrix, is 210 by 160. 210s are rows and 160 are columns. So that's a very small database. It will require very less memory. So now let's have a look on the image database that I'm using for this retrieval. So to train the model, we need several images. So an image database is needed. So for this problem, I have taken an image database of flowers. So this database has total 210 images. Each image is of RGB in the RGB format. It's a color image and it is with BMP extension. And the size of the image is only 128 by 128 pixel. These are some images from this database you can see. So various flowers of different kinds. This database you can download from my website, that is exptech.co.in. Okay. Now testing procedure. Testing procedure means I will give the query image and I will see that how effectively my proposed algorithm is giving me the nearest matches. So this is my query image, and first my system or proposed algorithm will extract the features of this image. So let's say this is my query vector FVQ, which has the length 160. This is my feature database X, which has already features of 210 images. So the feature vector FVQ of the query image will be matched with each feature vector in this feature database. So on the basis of the similarity, I will find the n number of nearest matches from the database. So these are my retrieved images. So they will be matching with the query image in the contents. So the similarity I am finding on the basis of the L1 distance between the query feature vector and the previously stored feature vectors. So I hope you know what is L1 distance. So now let's see the MATLAB implementation. So to implement this project in the MATLAB, first you have to create a folder. That will be the database folder. So I have named this as flowers. You can give any other name. So store all the 210 images in this folder. And also you have to do one pre-processing. That is, you have to rename all these images as 1.bmp, 2.bmp up to 210.bmp using some batch processing. If you are expert in the MATLAB, you can write the code, or you can do this with help of some batch processing image software such as Irfan View. So since I have stored all these images on my website, so when you download it, you will get already with these names 1. 2. like that. So there is no need of doing any pre-processing or batch processing. So now you have to create the three MATLAB files. The first file is the colef.m, this one. So this is the function file that will compute the feature vector. Okay. The second file is the testceh.m. So this will be used for testing procedure. You will give the query image here and you will get the n number of nearest matches. And the third file is the train.ceh.m. This file will include the code for training algorithm. I mean, you will find the feature vectors of all the 210 images in a database, and you will store all those features in a feature database, I mean the feature matrix. So let me show you the code of each file one by one. So, but before going that, this is the important thing, that you have to keep all these 3 M files in the same folder where all these image files are residing. So that is very important, otherwise your code will not run. So now this is the code for your function file, which is extracting the feature from the image. So this is the function declaration where I am passing the image. Here I am declaring the wavelet type COIF5 and then wavelet extension mode, that is periodization. And here I am getting the YCBCR components of the RGB image, then separating these YCBCR components, and then I am applying the Kenny operator on the Y component. Okay, and then by applying the Kenny operator, I get the binary image. So I'm converting that into the unsigned integer 8. So I can combine this with the CB and CR. So CB and CR are unchanged, so I'm taking them as it is, while this edge map is I'm taking here. So I have replaced this original Y with this Y edge, and then I am concatenating them again to get the P image, that is a YCBCR image. So converting that image back to the RGB with YCBCR to RGB function, I am getting this Q image. From this Q image, I am separating the R, G and B component. Okay. So now I am finding the histogram for R, G and B separately. So this is HR, HG and HB. So HR, HG, HB are the histograms of RGB components respectively of the length 256. So to reduce the size, I am doing the wavelet decomposition of HR, HG and HB. Here HR and HG are decomposed up to the level 2, while blue histogram is decomposed up to the level 3. So now I am extracting the approximation coefficients. Okay, so so I can get the feature vector. So AR is the approximation coefficients of red histogram up to the level 2, and AG is AG is carrying the approximation coefficients of green histogram up to the level 2, and AB will carry the approximation coefficients of the blue histogram at the level 3. So once AR, AG and AB are found, I have concatenated them to get a complete feature vector FV, whose length is 160, because 64, 64 plus 32. And this is a file, second file, which is used for the training. I mean, all 210 images are converted. I mean, we are getting the feature vectors of each image and then storing them in a database. So I have defined the number of training image 210 and the length of the feature vector 160. So I have first initialized this X matrix, which will be known as a feature database. So inside a for loop, I am reading one image at a time and then passing that image to the previous function file, which I have just discussed. So that's a function file, I mean color feature. Your color features are extracted and that will be stored in the locations of matrix X. So all 210 images will be represented by their respective feature vector. This is the third program, test.ceh.m, which is used for testing. So here you will give your query image and you will retrieve the nearest matched images. So first defining the number of trained image 210. Then with this code, a system dialog box will appear. With help of that, you can choose any query image. Okay, so that will go to IMG variable, then passing this into this function where the feature vector of this query image will be calculated and will be stored as FV. So now we are initializing a distance array where the differences will be stored. I mean, this calculated feature vector FV will be compared with all the previously stored 210 feature vectors, and the differences, I mean the L1 distance, will be stored in this difference array. So inside this for loop, you can see that this L1 distance is found. This is simply the element to element difference, and we are getting a summation of those differences to get the final difference. So once all the 210 differences are computed, this array is sorted in the ascending order. It means the lowest difference will be at the first position. So that will be the best match. So on the basis of the first 6 matches, the first 6 differences, I am retrieving these images and I will display all these images as a output. So with help of these, I am show with the obtained index number, I am showing the first image, second image, and similarly the third image, fourth, fifth, and sixth image. So I will get all the images. So now let me run this code in the MATLAB, and where I can show you that how this program is performing. This is the MATLAB, and this is my editor. So here I have written the function file already. You can see colef.m. So it is the same code which I have already explained you. And this is the training file, and this is the testing file. So first I will run the training file so that I can compute all the 210 feature vectors. So let me run. So I'm pressing this run button. Okay, so it is running. You can see this icon. So it is in action. You can see MATLAB is busy. Okay, it is done because number of images are very small, 210. And depending on the speed of your computer, it can be done in few seconds. But the number of images are very large. Obviously, it will take time. So it is done. And now come to the test program. So when I will run it, a system dialog box appear and it asks me to choose any file as a query image. So I choose, let's say this image number 15. So when I choose this as the input image, query image, let's see the output. Okay, so this is the output. The first one is the query image, and these all 5 images are the nearest matches which are retrieved from the database. So this is the first match, this is the second, third, fourth, and fifth match. So you can see the strength of this proposed algorithm. You are getting the 100% correct answer. Now let me run this program again, and let me choose another image. Let me choose a 21. Open, and yes, this is the output. So again, you can see that all 5 images nearest are the nearest matches, and it is 100% accurate. I'm getting the relevant output. On the basis of the content. So contents I've defined in the terms of color and edges. So let me run again. Let me choose one more. This 26. It's a complex shape of this butterfly flower. Open. Okay, so I'm getting this output. Very impressive. So this is my first one is the query image, and these are the first 5 nearest matches. So you can see that I'm getting the correct flowers as well as the color also. So that is content based retrieval. Run again. Let me take more. Let me take this rose 81.bmp. Open, and yes, you can see the output. So I'm very much impressed with the first match. So in the query image, you can see that there are 2 roses, and in the first match I'm getting the 2 roses. So that is the best match which I can see. And the rest of the images are also of roses and of red color. That is very nice. Let me run again, and I can take some complex. Let's say this purple one. It's a very complex shape, 44.bmp, and this is the output. Again, very impressive output. So this first one is the query, and you can see all the images are very much relevant. 100% accurate result I'm getting. Run again. Let me try one more. I can give this 90.bmp. This white color, or we can take something else. Yeah, this one 90.bmp. Open it and see, this is the output. Again, 100% accuracy, color, edges, everything. Run again. Let me test few more. I can take this one, this pink one, 165, this pink flower. Okay, once again I'm getting 100% accurate result on the basis of type of flower and the color also, right? And run again, a few more from the last few images. I can take some white flower. Okay, this one, 198. Let me take 198. It has some complex shape. Okay, once again I'm getting very good result. Very good result. And one more, the last, let's say 147. Open. Okay, so it has one very slight mismatch, this third match, but on the basis of the color it is okay. All the results are okay, but the first and fifth match is 100% right, while second, third and fourth, they have some differences, but look wise you can see the results are almost same. So this is the effectiveness of this approach propose algorithm, which is very simple to implement. The code I have already given you, so you can implement this for your project work. So this proposed algorithm is very fast because the feature vector size of the feature vector is very small, that is 160 only, and it requires that, because of that it assists us to get the faster search, as well as it requires the less memory. So I hope you have enjoyed this video and you have learned how to implement a simple CBR system on the basis of edges and the color feature. So thank you very much for watching this video. I hope you have enjoyed, you have learned something new. So I request you to like this and subscribe and spread this video to as many as people so they can get advantage from it. So thank you very much once again. Have a nice time.